Alright, let's go ahead and take a look at another way that we can handle conditional probabilities, and that's with Bayes' rule. Bayes' rule gives us a way to handle a backwards conditional probability. So what I mean here by backwards is from the information that we've been given, we will know the probability of, say, the probability of F given that E has occurred, but then we will want to know the probability of E given that F has occurred. So we're going to want to know sort of the opposite order. So that's why we think of this as like a backwards conditional probability. The formula is a bit messy. You can see I've written one version of the formula here, but we can sort of simplify this a lot if we use a tree diagram. So whenever you're trying to do a Bayes' rule type of problem, you're going to want to start with a tree diagram. And so we'll go ahead and approach it in that direction. Basically, the idea with Bayes' rule is if you want to know the probability of E1 given that F has occurred, and E1 and E2 are mutually exclusive events. So that means that their union is the sample space and they don't overlap each other. And we're going to let F, excuse me, my goodness, let F be any event in the sample space with the probability of F not equal to 0. Then what we can do is if we want to find the probability of E1 given F, we will look at the intersection of E1 and F and the conditional probability of F given E1. And then we'll divide this by the probability of E1 times the probability of F given E1 plus the probability of E2 and the probability of F given E2. So let's look at this, how this actually applies with an example. So we have a virus, a certain virus infects 1 in every 200 people. So we know that the virus will infect 1 in every 200 people. A test used to detect the virus yields a positive result 80% of the time if the person has the virus, and 5% of the time if the person does not have the virus. So this means that we're getting a false positive. So 5% of the time, if the person does not have the virus, the test will still say that they do have the virus. So now the question is, if a person tests positive, what is the probability the person is actually infected? So we are assuming that the person is testing positive, so this is our assumption. And then we want to know what's the probability that they're actually infected. So we're interested in the probability of being infected with the virus given that you tested positive. So our assumption here is that somebody is positive. However, all of the information that we've been given, the assumption has been the person either has the virus or the assumption is the person does not have the virus. So we do not have the same information. Instead, our probability that we're trying to find is going the other direction. We are assuming that somebody has a positive reaction to the test, and then we want to know what's the probability they are infected, versus assuming that a person is infected and then seeing the probability that they have a positive reaction to the test. So this is an example of that backwards conditional probability. We know information that assumes the thing that we are now trying to find the probability of somebody being infected. So let's go ahead and organize a tree diagram so that we can figure out how these different things are going to relate to each other. So first, we're going to start with the probability that we are actually interested in. So we want to know the infected level. So we're going to start with the probability that somebody is infected. And notice that that is the assumption for the conditional probabilities that we have. A person has the virus or they do not have the virus. So that relates back to being either infected or not infected. So at the first level of our tree, you can be infected or you can be not infected. Now, the probability that you are infected, and actually let's just rewrite this, infected versus not infected. There we go. So the probability that you are infected, we know that the virus infects 1 in every 200 people. So there's a 1 in 200 probability that that somebody will be infected, and so that means there is a 199 out of 200 probability that you are not infected, because everybody's either infected or not infected. Okay, so now let's see the next level. If somebody is infected, then if they take this test, they can have a positive result or they can have a negative result. If somebody was infected, they get a positive result 80% of the time. So if we have assumed that the person is infected, then they will yield a positive result 80% of the time. So that would be 80 out of 100, or we can write it as 0.8. That means that 20% of the time, so 20 out of 100, is the probability that somebody is infected, but the test gives a negative reading. So it doesn't say that they are positive for the virus. Let's see, if somebody is not infected, then 5% of the time, that person will get a positive reading on their test. So if somebody is not infected and they take the test, they can still get a positive reading. They can get a false positive or they can get a true negative. The probability that they get a false positive is 5 out of 100, and so the probability of a true negative would be 95 out of 100. Okay, so now we've got all of our different pieces here. We want to figure out basically what is the probability that we are actually interested in. We want to know the probability that somebody is infected given that they had a positive reading on their test. And so if we sort of follow our formula that we have right here, we're going to take the probability that somebody is infected and we'll multiply it by the probability of somebody being positive and infected. Positive given that they are infected. And then we will divide by the probability of somebody being infected times the conditional probability of a positive reading given that they are infected. And then now we're going to also add what's the other way that we could get a positive reading. Well, we could be not infected, and then we'll multiply that by the probability of having a positive reading even though we are not infected. So we're essentially dividing by all the ways that we could end up with a positive reading. And then the outcome that we actually want is the one that goes in the numerator. And so the way that you can sort of keep track of this, that you can keep this straight, we are looking for the infected and positive outcome, right? We want to know what's the probability that somebody is infected given that they were positive. So we're looking for positives on the outcome. But there's also the not infected and positive outcome. So we basically have two branches that we need to consider from our tree. And that's what the multiplications are doing. They're giving us all those different branches. So the probability that somebody is infected, this is coming from our first branch right here. Somebody could be infected. That probability is 1 out of 200. So we get 1 out of 200 times. Now the probability that somebody has a positive given that they were infected. Well, that's the second part of our branch. That's the 80 out of 100. And there's our first branch. This is the desired branch. So this is the branch that we actually are interested in the probability of. And now we have to divide this by the total number of ways that we could have had positive. So we will include the same branch that we've just looked at, but we will also need to include the other branch, which is not the outcome that we are looking for. So we will have, again, 1 out of 200 times 80 out of 100, and then plus, now we're looking at branch number 2. The probability of not being infected is 199 out of 200 times the probability of having a positive reading but not being infected, which is 5 out of 100. And so let's see, if we multiply this all together and divide, we should end up with 16 out of 215. So we could leave our answer as a fraction or as a decimal. This would be 0.074. So either of these results is an appropriate final answer. Now let's think about what this means for a moment. This means that the probability that so if you have a positive reading for this test, there's only a slight 7% chance, 7.4% chance that you are actually infected. So that's, you always want to get a second test because a test isn't necessarily 100% accurate. And so just having a positive reading is not really enough to make sure that you are actually infected with the virus, because you could have a false positive, like we see here. All right, that's all for now.